Welcome to this lecture video. In this video, I am going to explain elastic properties of materials and also the relationship between elastic constants, which comes under module number 2 of engineering physics prescribed by BTU. Let us discuss the following points. So here we are going to discuss about expression for bulk modulus K in terms of alpha and beta, expression for rigidity modulus, and relation between Young's modulus, rigidity modulus and bulk modulus K. And let us look at what is the relationship between bulk modulus K in terms of alpha and beta. Here alpha is longitudinal strain coefficient and beta is lateral strain coefficient. Now let us look at the expression for bulk modulus in terms of alpha and beta. So alpha is nothing but longitudinal strain coefficient. It is nothing but longitudinal strain produced per unit stress. Whereas beta is nothing but lateral strain coefficient, that is lateral strain produced per unit stress. So that's what the meaning of alpha and beta. And bulk modulus K is nothing but it is the ratio of bulk stress to bulk strain within elastic limits. So that's what explained here. So longitudinal strain coefficient alpha is the longitudinal strain per unit stress. Lateral strain coefficient beta is the ratio of lateral strain per unit stress. Now let us consider a material in the form of a cube as shown in picture. Here OX, OY and OZ are having equal dimension, and the volume of this box is considered as 1 in the beginning. So original volume is taken as 1 unit, and this box is subjected to outward force, that is Tx acting along x direction and Ty acting along y direction and Tz acting along z direction. So that you can see in this picture. So this is the outward force. Because of this force, there will be an expansion in the volume of the material. So because of the force Tx, there will be increase in length along x direction, and at the same time contraction is going to happen along y and z direction. And because of the force Ty, there will be an increase in length of the material along y direction, and parallelly there will be a contraction appear along x as well as z direction. And because of the force Tz, there will be increase in length going to happen along z direction, and parallelly contraction is going to happen along x as well as y direction. So in order to calculate the change in volume of this material, let us look at the further equations. Now let us consider the cube subjected to tensile stresses, that is Tx, Ty and Tz along x, y and z axis. Due to these stresses, the dimension of Ox, Oy and Oz were all altered. The altered value of Ox will be written as 1 plus alpha Tx minus beta Ty minus beta Tz, and the change in or altered in length along Oy is given as 1 plus alpha Ty minus beta Tz minus beta Tx, and the altered length along OZ will be 1 plus alpha Tz minus beta Tx minus beta Ty. See here, alpha indicates extension or expansion, whereas beta indicates compression. So that's what the symbols appear in the equation. So Ox is nothing but 1 plus 1 is the original volume plus alpha Tx minus beta Ty minus beta Tz, and along Oy 1 represents the original length along Oy of the box, and 1 plus alpha ty minus beta tz minus beta tx. Similarly, along both sides it is 1 plus alpha tz minus beta tx minus beta ty. So these were all the changes going to happen along x, y and z direction of the box because of the outward forces happening upon it. Now, in order to calculate the change in volume of the box, let us look at the further equations. So the final volume can be written as 1 plus alpha minus 2 beta into Tx plus Ty plus Tz. So here, by neglecting the higher order terms of alpha and beta, and we have to consider Tx is equal to Ty, that is equal to Tz, that is equated to T. So if you consider that, the final volume of the box will be equal to 1 plus alpha minus 2 beta by 3t, that is alpha minus 2 beta into 3t, that is the final volume. Therefore, volumetric strain can be written as final volume minus initial volume. So if you calculate that, it will become alpha minus 2 beta into 3t. Further, the bulk modulus of the material can be written as T by alpha minus 2 beta into 3t. Then on simplification, we can write the value of K is equal to 1 by 3 times alpha minus 2 beta. Here T cancels. So this is what the relationship between bulk modulus K and alpha and beta. That is K is equal to 1 by 3 into alpha minus 2 beta. And let us look at the expression for rigidity modulus. Now we have to consider a cube of uniform length. Let L be the length of the cube in all direction. The bottom face of the cube is fixed here and it is subjected to a tangential stress T along the top layer. So under the action of tangential force, the cube gets deformed to A dash, B dash, C D as shown in picture. The shearing strain is equal to theta and is given by theta is equal to BB dash, that is BB dash by BC. So here BB dash is equal to L and BC is equal to capital L. Therefore, the shearing strain or shearing angle theta can be written as BB dash by BC or which is equal to L by L. So this box is fixed at the bottom layer, that is the bottom layer DC is fixed and the top layer is subjected to shearing force that is towards x direction, that is T. So because of this force T, the box is tilted through an angle theta as shown in picture. And the value of theta is equal to BB dash by BC. And further, as according to Pythagoras theorem, the length BD is equal to root 2L. And because of the force applied T, the point A is shifted from A to A dash and point B is shifted from B to B dash. And the angle theta is observed to be BB dash by BC. So this is what going to happen in this material. If alpha is linear strain per unit stress and beta is lateral strain per unit stress, the strain produced along the diagonal BD will be equal to T into alpha plus beta, that is equal to MB dash by BD. Further, MB dash is equal to BB dash cos of the angle BB dash M, which is equal to BB dash cos 45 degree. So here the angle BB dash M is equal to 45 degree. Therefore, cos 45 degree is equal to 1 by root 2. Therefore, the value of MB dash is equal to L by root 2. And further, the value of T into alpha plus beta can be written as L by root 2 divided by L into root 2. And further on simplification, we will get the value of T into alpha plus beta is equal to L by 2L. That is small l by 2L and which is equal to theta by 2 as according to the diagram. Further, T by theta is equal to 1 by 2 into alpha plus beta, that is equal to rigidity modulus n. Therefore, the rigidity modulus n will be equal to 1 by 2 times alpha plus beta. And now let us concentrate on what is the relationship between Young's modulus, rigidity modulus and bulk modulus K. So we know that bulk modulus K is equal to 1 by 3 into alpha minus 2 beta. That is equal to 1 by 3 alpha we have to taken out as common in the denominator. So we get 1 by 3 alpha into 1 minus 2 sigma. Here the value of sigma is equal to beta by alpha. Further, the value of 1 by alpha is equal to Young's modulus. Therefore, the value of K can be written as y by 3 into 1 minus 2 sigma, or 1 minus 2 sigma is equal to y by 3k. Consider that as equation number 1. Further, n is equal to 1 by 2 into alpha plus beta, that is equal to 1 by 2 into 1 plus sigma. Here 1 by alpha is equal to Young's modulus, therefore the value of n is equal to y by 2 into 1 plus sigma. So 2 plus 2 sigma is equal to y by n. Consider that as equation number 2. Now we have to add equation number 1 and 2, and after simplification we will get the value 3 by y is equal to 1 by 3k plus 1 by n. So this is what the relationship between Young's modulus y, n and k. Thank you.